In this lesson, we're going to learn some definitions and theorems to find the lengths of right triangles. So mean proportional is the same as geometric mean. So these two words can be used interchangeably. Now this mean is not like mean, median, mode. So let's write this definition in your notebook as well as the proportion and all the components. So the geometric mean of two positive numbers, a and b, is the positive number x such that a over x equals x over b. Now, one of the main important parts of this is knowing the components of this geometric mean. So the extremes is the top left and the bottom right, and your means is the bottom left and the top right of your proportion. And you're simply going to use cross multiplication to find your answer. So notice that the means will be the exact same value. So let's practice. It says find the geometric mean between 2 and 18. So we're trying to find the means here. It says find the geometric means. Remember, the means are the bottom left and the top right. So you're simply going to cross multiply. And so we're going to have x times x. We have x squared equals 2 times 18 is 36. And now we're just going to solve. My x is positive or negative 6, but we're just going to consider the 6 in our answers. The next one, find the geometric mean between 6 and 12. So again, we're trying to find the means. That's these values here between 6 and 12. 6 times 12 is 72. We're going to take the square root. I'm going to go ahead and just do plus or minus, but we're only going to consider the positive. Now, 72 can be broken down into 36 times 2. The square root of 36 is 6 roots of 2. Again, we're just going to consider the positive when we're referring to these because we're going to be looking at triangles and lengths, and we're not going to have negative lengths. Okay. So a couple of theorems and definitions before we apply the geometric mean to right triangles. So let's write this in your notebook. The altitude to the hypotenuse of a right triangle. So the altitude, which is this line CD. So the altitude to the hypotenuse of a right triangle forms two triangles that are similar to each and to the original triangle. So we're going to break this down, but again, just go ahead and get this in your notebook. This theorem, as well as the definition of an altitude. An altitude of a triangle is a segment from any vertex perpendicular to the line containing the opposite side. So let's get a color that will show up. So this again, right here, in this problem here is an altitude. It's going down and it's perpendicular. So it's going from a vertex to a side opposite, and it's perpendicular because we can see that it created a right angle. So CD is our altitude. Now, if you can kind of envision, we have three similar triangles going on. We have the biggest one, which is ACB. So we have that triangle. Then we have the medium triangle, which is ADC. So that's the medium size. And then we have the small triangle CDB. And these triangles are all similar to each other. Again, that's what this symbol right here, this means they're similar. Okay, let's show where I separated the triangles to show similarity. So again, we have the big white one, which is this big pink one. And then we have the medium size and then the small size. So these three triangles are similar to each other. Now we're going to get into two theorems that deal with this situation where we have an altitude of a right triangle that creates three similar triangles. So let's write this in your notebook. The altitude to the hypotenuse of a right triangle is the geometric mean between the segments into which it divides the hypotenuse. So I know that's kind of wordy, but after you write the theorem down, go ahead and write your rule. This is the altitude rule. Okay, we're going to apply the altitude rule to find some missing parts of our right triangle. So we're going to use the altitude rule, yes, when you know the altitude. So here's our altitude of 4. Okay, so here's your altitude rule when you have part of the hypotenuse and another part of the hypotenuse, and then your altitudes, that's going to be your means. So here we're going to set this up. So we're looking at the big triangle. Our hypotenuse is 8 plus some other length, x, and then we have our altitude of 4. So when you know your altitude, this is the rule that you're going to use. So we have part of the hypotenuse, which is 8. We have our altitude, which is 4. And then we have the other part of our hypotenuse, x. So we're trying to find the value of x. So we're just going to simply cross multiply. And solve for x. So x is 2, but if it wanted to know the total hypotenuse, it would be, so AB would be 10. Okay. Another part of using the geometric mean is the leg rule. So let's write this theorem in your notebook. The leg of a right triangle is the geometric mean between the hypotenuse and the projection of the leg on the hypotenuse. Again, I know that's kind of wordy, but just write that in your notebook along with your diagram. And then our leg rule. So the leg of a right triangle. So let's talk about, and we have two options here, the leg in the yellow and the leg in the red. So we'll focus just on this long leg. We'll talk about long legs and short legs further into this lesson. So here's the long leg of our right triangle. And then here, this part is called the projection. It's not the whole hypotenuse, it's just that part of the hypotenuse. If we were considering the yellow leg, then this would be the projection that corresponds to that short leg. So we have leg and projection. You can either use that information, or if you wanted to use the short leg information, this is the short leg and its projection. And again, the leg is going to be the mean. That's going to be here. So in this proportion, is the hypotenuse compared to the leg is equal to the leg compared to the projection. So here's our leg rule. So here we have this large right triangle, and we do not have the altitude, so we can't use the altitude rule. So we're going to use the leg rule. So our leg, and we're using the long leg, is x. So that's why we're going to put x. Those are the means. And then we have the 4 is your projection, and 9 is your hypotenuse. Okay? So we're going to put 9 as your hypotenuse, and then the projection, which is just part of the hypotenuse. It's going to go in this part of your proportion. And now we're simply going to cross multiply and solve. And you see why that we will only consider the positive, okay, because we're talking about a length. So this leg is 6. Now, if we wanted to find this leg, we can do the Pythagorean theorem, which we're going to take a look at in just a second. As of now. So if we wanted to have found that short leg, we would apply the Pythagorean theorem. So I'm sure you have studied this, but let's go ahead and write it down again. The Pythagorean theorem, it says in any right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. Remember, your legs create the right angle, and your hypotenuse is always across from the right angle, and the hypotenuse is always the longest length. So here, we know the hypotenuse and we know a leg, and we're trying to find the long leg. So we've plugged this into our theorem. And again, I'm only going to consider the positive because we're talking about a length. So when we break down 80, that is 16 times 5. The square root of 16 is 4 roots of 5. So sometimes they want the exact answer, which is a radical answer, if it's not an integer. And sometimes it may want a decimal, and it'll tell you to round to the nearest tenth or whatever, and then you can just plug that into your calculator.